your time again. So yeah, last week I presented something about only spin transfer torque. So today I'm going to present like more what I'm doing in one of the tasks I am committed to. So yeah, again, this is our group. So we are a theoretical group, like quite big. We work in different branches of physics. Yeah, so we do work with spintronics in general. So atomistic simulations, but we also go to like magnetic simulations. And there are people that works with polaritons and also other stuff. For that, we also use these high performance computing clusters. So yeah, just a general overview of our group. But yeah, so today what I'll talk is just yeah, so Lonawi-Schitt-Gilbert equation. I'll start and say something about analog black holes, and also after that magnonic black holes, and then we will discuss a bit of double hole cavities, and then what can I do, or yeah. So yes, as I mentioned last week, this is the Landau-Lifshitz-Gilbert equation. So yeah, this part is like everyone, I mean, a lot of people is already used to it. But then yeah, there is also this term that is related to current application. And yes, as I mentioned yesterday, so the classical picture, if you remove the SCT, is like you have the magnetic moment, and then if you apply the field, then you have the rotation. But in this case, the rotation will be negative here. And then, of course, in the early 20th, Gilbert, he proposed this term here, which is something like, yeah, you should have a damping here because your oscillation otherwise will continue processing. And then, yeah, so after a bit, yeah, this term was proposed by Zhang, but actually the experiments for that is like quite old, is like before the 20th. Yeah, also this effective field is something that is important for us, and it can be related to many effects. For instance, just look this one. So here we have like the exchange constant, we have the uniaxial anisotropy, and also external field. Yes, the signs here, they are also important because they are related to if you're minimizing or maximizing the energy of the system. Yeah, so yeah, you can write the Zhang equation, which is this term here. And then if you apply current only in one direction, you can get like this pretty beautiful equation. So yes, if you, for instance, consider this effective field here, you can write this matrix here. And then, yeah, if you use this Bolyubov transform, you can end up with this equation here. There'll be also some differences. If, for instance, you, instead of ky, you consider the kz, so you might have the off diagonal terms here as well. Yeah, so wait. So in general, this is the picture that we will use if we want to study like how the direct current should modify the propagation of spin waves. In this case here, yeah, this is just the linearized version. So it's the dispersion relation. We can, it's something that's very useful. So we can study like how the spin waves are propagating. And yes, people are already doing that, but yeah. So in this case, this is a work made for my co-advisor actually, and he was studying how we can have, for example, different kinds of refractions, and he also got this like total reflection, which is a case we studied in like high school. Also, he used the current to, for example, do the like tune the path for the spin waves, and then it can be used to like choose different outputs. Of course, there is already a bunch of experimental works. This one is the most famous one. So it was like showing how you can get the Doppler shift, which is the variation of the frequency due to the applying of a current in a spin wave propagation. And also there is another one, this one here, where they show that depending on the thickness, you can also have different Doppler shift. Actually, if you increase the thickness, so your Doppler shift will reduce and so on. Yeah. So we will use this effect that I just showed here, so spin transfer torque, because it is actually related to the magnetic black hole. So, but before talking about magnetic black holes, we have to talk about analog black holes. So, in 1974, it's a very famous paper. So Stephen Hawking, he showed that so you can have creation of particle and antiparticle in black holes. So you must study that with like quantum mechanics, and then just right after that, so this Canadian professor here, he wrote this paper showing basically that, okay, so we can also have the same effect, but for example with sonic waves, and it's actually very easier to see this effect, so why not? And then he proposed some experiments that the first one was done in 2004, but yeah, this was the first conference related to analog black holes, and it was done in CBPF in 2000, so yeah, Brazil was there. Anyway, so nowadays, for the picture of analog black holes, we can have analog black holes in many physical systems. So we have like for sounds, we have for hydrodynamics, we have like shallow water. This one is very interesting. There is a lot of groups doing these things with waves. There is, of course, the ones related to refractive index, and there is many others related to quantum. But in general, if you want to like have an analog black hole, the thing you need to do is like you have to tune your dispersion relation, and then you have to like work with really low frequencies, or you can also use high frequencies, but then the way you have to tune these frequencies have like this background velocity here, you have to increase it a lot, so then you can tune your dispersion relation to go below zero, because in that sense, for example, speaking about electromagnetic, you will have like you have the super radiance. So once your wave crosses this part, then in this region here, you can call it that is a black hole. Yes. So yeah, but back then there was no proposal for like magnetic black holes, and then so. But by considering this equation here, you can see that this equation here is for like shallow water. So, and then yes, you can see here there is this term here that you can tune, and then you can reduce the frequency. And actually this term here is quite similar to the ones I showed you here. So in this case here, we have this velocity here, which is connected to the current that you need to apply to the system. So let's go forward. Yeah, so yes, so in 2017, this paper was presented for the group of Professor Dorn. And then he presented like the theory and also the calculations of how can you manage this, how can you create, for example, this magnetic black hole. So in his proposal, what he said was like, so you can have the spin wave propagation. Let's suppose you have the spin wave propagation, and then you can apply current in your system. But let's say this region here, you can reach like a critical velocity. So if you are above this critical velocity, the spin waves that crosses this region here, let's call them event horizon. And then so if the spin waves they cross these event horizons, you can have like the existence of this magnetic black hole. And because it's easy to be tuned, so you just need to change the polarization. You can have either black hole, white hole connection, or you can have the opposite of that. So in this case, if you send, for example, spin wave from left to right, you end up with like the spin wave will cross it if you have like the black hole on left, but then there will be some kind of interactions with the in this cavity, let's say, and then it will also result in another kind of radiation that will be sent here. So usually when people work with like black holes or other kind of analog black holes, one thing that is very that they are very interested is like to study, for example, Hawking radiation, and that can happen when you have like particle and antiparticle interactions. Yeah, so after that, the same group, they developed way more the idea. So they proposed this kind of sample where you can have like you have a ferromagnetic stripe, and then you apply current, and then because of the way the geometry is, so in the center you have way more current than on the edges. So if you have the dispersion will be like this in this part, and then when it goes to the center, because of the increase in the current, your dispersion will do this, so it will go below 0, and then after that it will be the same. But in this part here, this interaction with this current will modify the spin waves. And they also presented that, okay, so in this case here, yeah, so you have y on what we usually call z. But anyway, so if you change, for example, the anisotropy in this out of plane, you can have like an increase on your transmission coefficient, and that is something that I will also present you in the end. So yeah, but yeah, so before I go on, another thing that is very interesting and helps us a lot when we are studying like spin wave propagation in this kind of situation is like to understand space-time diagram. Yeah, so I just put these like really easy to understand space diagram. So yeah, so we have here, in this case it's velocity, but yeah, you can also have time on the y-axis and then space here on x. So the thing is, what is important here is like to understand that as the curve goes down and down and down, it means that actually your spin waves are like getting faster. Yes. Another thing is like in this case, it's all inertial frame, so there you're not tuning the space, let's say. But yeah, so if you apply homogeneous current, for example, you can tune this thing. So you can start with something like this, and then at some point this curve will bend. And what is important here is, for example, if this curve bends to like 0 or close to 0 slope, it means that your spin wave velocity is like very fast, is like going to infinity. So it means you're close to a black hole. And then you can also have the opposite. So if you have the white hole black hole cavity, what will happen is like your spin wave will go like this, but it will go to the top. So it will go vertical, and then what it's supposed to happen is like your spin wave will not propagate anymore, but that's another thing I will show you, and we can also discuss. Yeah, so this is the simulation parameters we used. So yeah, again, this is the picture because it's a very nice one. So we had an antenna here in the beginning, and then we send a spin wave through it. We generate an R field oscillation here, which generated the spin wave propagation. And yeah, so we did this for different widths. And yes, so we also calculated the current density, the current distribution for different constrictions. So which made it easy for like understanding this continuous effect. Okay, yeah. So we started everything just looking for at the dispersion relation. So in the dispersion relation, we have like, so we calculated here just the rectangular stripe, the dispersion relation. So what we did here, we just calculated the dispersion relation for very low field. So because the fields are very low, so you can see each branches are almost close to each other. So it's not zero, but they are very close because the field is like 0.1 millitesla, so it's very low. Yeah, but what we can see here is as we change the current here, the current is calculated by this expression here. So as we change the current here, the dispersion curves, they start to bend from one side to the other. And then we have here, so this is zero current, this is like the critical current, and if we increase and increase the current, we can reach out also this effect here. From now on, we will look for this case here, because the thing is, this case here, we can see that there is an interaction between each branches, and it's very clear. So to calculate this thing, we just send a sinc field because it contains all the frequencies. But to study how this effect works, we can send like fixed frequency. So we can send like a sine field. And if we send like a sine field with, for example, 100 megahertz, we can see that this spin wave will interact with both branches, and I will just show you what comes next. Yeah, so in this case, we started to study the inhomogeneous current. Yeah, so one thing we did, one consideration we did in this part was like, so this is the current distribution for the constricted geometry, the most constricted one, this one. But yeah, because if the spin wave is excited here and it goes through, all through the way, the spin wave will be concentrated. So we didn't want to see this concentration because it would be like hard to understand what is going on. So we took this current distribution in the center, and then we set it in a rectangular stripe. So yeah, and this is what we see here. So depending on the frequency sign that you send, and all the results here are with the same scale. So for example, 500 megahertz, you don't see really a big effect of it. Yeah, in the left, we have like positive current, which generates the white hole and the black hole here. And with the negative current, we generate the black hole and the white hole. We did this way, and most of the things we did was looking for the white hole and black hole cavity, because it was easy to see where you have this effect. So yeah, for example, here we can see that for 100 megahertz, you have this part where the spin wave just disappears, but then it comes back in the other side. So we are still trying to figure out like what could cause this effect, because yeah, and if you reduce the frequency, of course it is still going on here, the thing. And yeah, for negative current, yes, we have the same, we have the opposite effect in that case. So the frequency will go, as I mentioned to you. So if you look for the space-time diagram, you have like a stripe where if we don't have current, it should be something just a diagonal line. But then because we have this inhomogeneity with the current, so we're changing the background velocity, then the spin wave will just bends it, and then it comes back again in after this region. Yeah. Yeah, so in this case here, we did just a simple study, which was like, we created a barrier like a current distribution, and then we send spin wave from the beginning, and we try to see what happened. Yeah, so without current, we see that the spin waves just go all the way through like diagonal. But if we have like positive current in this part, so in this case we don't have a double hole cavity, but we have only one cavity. And in this case, for example, the spin wave, after crossing this part here, it disappears because the current just will make the spin wave, the wavelength, to become smaller and smaller until it disappears. And here, of course, in the opposite case, we have like an almost zero slope as it crosses this region here. Yeah, so we also did another kind of study for different geometry. So we changed this constriction size for like, this is 0.1, 0.2, and 0.4. And then we try to see, yeah, sorry, 0.2, 0.4, and 0.6. And then we try to see like how this constriction would be affected. And as you can see here, the current was not the same, but this was because if we set the same current, for example, in this case, we have these event horizons, but in this other case, we wouldn't have it because they are big, so we wouldn't have any event horizons. So we had to increase it a bit. Yes, so this is a thing we are still trying to see how to connect with other results. Yeah, but yeah, so another interesting effect is that, okay, so we all know that if you apply the current, you can tune this dispersion relation. It's already known. And we also, there is also theoretical works showing that if you apply DMI, you can have the same effect. But yes, could this also work for, let's say, creating these critical effects? And then we did the study like only, so we had like a really low current applied here, like 0.5 teraamperes per meter square. And then we applied we changed it a bit, the Dialoshinsky-Moria interaction. So, and we found out actually that we can just change the VS for this VDMI, and with this value here, we can have the same effect. So yes, as we change the DMI, we can have the same modification in the dispersion relation. So, but yeah, but the same modification that we see in the dispersion relation is not the same thing that we see if we look into the space-time diagram. So, for example, here we have like the DMI in this part, these black vertical lines, but yeah, it presents some effect. You can clearly see that it is working with the spin waves, but it's not really doing the same effect that we have, for example, when we apply the current. Because here in this case, we reduced the DMI and we apply the current, and considering this case, we have the same effect, like vanishing the spin wave in the center and then it comes back again in the other side. And also for the negative effect, we have the same thing, like we get an enhancement of the spin wave here in this region where we have more current application. Yeah, of course, all these things that I presented to you are related to non-dipolar effects, because if we add dipolar effects, then the frequency will just increase related to like the square root of ms, and you guys know. But yeah, so we also try to see how would this effect would happen with considering dipolar interactions. Actually, there is already a work related to this. So you were just trying to see if we can get the same thing. Yeah, so with zero current, we'll have this kind of dispersion relation. Yeah, all the lines that I presented here in this one and also the previous are just the theoretical calculations that is already known. Yes, so you can apply current, and then you have this anomalous dispersion relation, and if you apply also DMI, you can get the same thing. So here I applied a really large current. This is all times 10 to the 12 amperes per meter square, so it's quite high. But then if you apply the DMI, you are able to reduce the current, because in this case here you have the same dispersion as as in B, but with way lower current. So it is something that can be engineered. And yeah, so this case is like we're using the same current as B, but with just a bit of DMI. So we see that the effect is enhanced. We can also calculate how this critical current changes with the thickness, because thickness is something important when you consider dipolar interactions. And then yes, if we just calculate it on Python, like we calculate the roots of this equation here, we can see that these roots will do something like this for different thickness. So yes, we can, yeah, I did of course calculations for 1 nanometer, but yeah, we know it's not really possible to do that experimentally. Yeah, so this was the first part with these results related to inhomogeneous current, but I will I will talk more about double hole cavities right now, which is something that is also connected to this, but we are still trying to see, because this is like a continuous effect. This is like a continuous effect, and in the other case it's a discrete case. So, and we are trying to connect. And anyway, so it all started with a paper, not this one actually, but this is in the first case. So what they did here, yes, they sent spin. They were investigating spin wave with a double hole cavity, but the cavity they did was like in the center. They set a current here, so, and they are only dealing with anisotropy, so there is no external field. So if they don't apply any current here because of the difference in the uniaxial anisotropy, the spin wave will just stop in the center here. But then if you apply a bit of current, then your spin wave will be able to transmit to the other side. And they call it like super mirrors and spin wave amplifications. It's a really nice paper. There's an animation they also present for this one, where you have like, you create the spin wave propagation here and it goes all the way through. And then it reflects here, goes to the other way, and then back and forth. Like we have, for example, in thin film interference. We see that like textbooks. Anyway, so but in the end of this work, they presented this idea here. So it was something like, what if we apply current only in one part of the sample, in a very small part, and if we change this length, what can we have here? So what they show is like, they have this effect here where you have this interference pattern. And then they finished the work. This was one of the last results they presented here. And in this case, there was no magnetic field, so all the results they were showing was related to like uniaxial anisotropy. And the second work I presented to you related to magnonic black holes. So they have this derivation here where they show like this transmission coefficient. It depends on this delta, and this delta here is connected to this uniaxial anisotropy. So as you modify the uniaxial anisotropy, you can have this enhancement on the transmission, which in this work we cannot see it because the uniaxial anisotropy was always the same, but we still see that as we change this length, we can have this interference pattern. So a bit later on in the same year, like one day before Christmas, they presented this work here where they show like you can have resonant amplification of spin waves in a black hole horizon. So what they did was, in this case, they used the dipolar spin waves, and then they propagate it, and then they change this length here. So what they show is like, depending on the constriction, depending on the size of your cavity, you can have this enhancement. So you can have resonant and also off resonant. So they send the spin wave right here, and then looking in the space-time diagram, you can see that as they go a bit in the part where they have this cavity, you can have the enhancement for some L values, but for other ones you will have like off resonance, so the spin wave will have no interactions with that. And yes, so both papers, they also say yes, this resonance can generate these Hawking radiation, and it can be connected to interactions with a magnon and anti-magnon. So what we did recently was like, we did a simulation a bit more robust, changing some parameters. So we changed the current for different values, and what we did was something a bit similar to what we have here. So we calculated the transmission coefficient, and then we variate the cavity length. So what we see here is that this cavity, as we change the cavity, we will have like resonance and off resonance points. For example, in the C here is this guy here, so we have like a really resonant peak, we can see it, and also E here, which is 350. But in the off resonant case, we have almost no interactions. So we were trying to understand why this thing would happen, and then the thing is, like, depending on the value of the current, you will have this effect or not. For example, if we reduce it a bit, like 2 times 10 to the power of 12, we will still have some kind of resonance peaks. But if we reduce to 1 or 0.75, we will have no interactions whatsoever. And then if you remember the dispersion relation that I was presenting to you in the beginning, the thing is, like, yeah, so the thing is, all of that interactions was like for 100. Okay, yeah, you can say it, please. Okay. Yeah, so all of these interactions here, we calculated for 100. All of those resonance mode we calculated for 100 megahertz frequency. And the thing is, so this is actually the 3 times 10 to the power of 12 ampere per meter square. So the thing is, this value here, we can see the interactions between these branches, the upper and the down one. And the upper one is related to the magnum, and then the down one would be related to the anti-magnum. So when we have this interaction here with both modes, then we have the amplification that we see on that figure. But if we reduce the current, then if we reduce the current, then the both branches, they will not be connected anymore, so you will not have the interactions that you see. So then both waves will just not have the resonance effect. So they will just be they will increase the amplitude, of course, because we have current in the center, but they will not have these interactions that is shown here. And another thing which is also in agreement with theory is, like, if you modify this out of plane anisotropy, you can have this effect more and more enhanced, so which is shown here. So depending on, as you increase the uniaxial anisotropy, these peaks can be higher and higher. All of these peaks were calculated for this current value, and yes. So yeah, the next steps that we can do is, like, we must improve the understanding of, like, how this discrete double hole cavity can be connected to the other one continuously. We also have to study how this temperature effect would modify this dispersion relation, because we know, of course, if we have constricted geometry and we apply current, there must be thermal effects, and we have to see how it could be, for example, engineered in order to enhance this effect. And yes, we can also explore alternative designs for these magnon black holes. For example, last week I showed you the Corvino geometry, but we can also engineer different kinds of constrictions. And yeah, also investigate potential application for stochastic behavior, of course, by considering thermal this thermal noise, and what would be easier for engineer, like spin wave lasing, and considering this, of course, non-uniform temperature gradient. Yeah, and these are my advisor. This is my co-advisor, and I thank all of these people for all the support. And thank you.
Thank you, Jean. Questions? Comments? Okay, so I guess we can just break out, take a break for our coffee break, and then we can discuss, and then we come back again. Yeah. All right.